We have to move now to our last speaker for this section, Professor Yusuf Rashid. Please go ahead.
Hello, Professor Salah. If you can allow me to share my screen, please.
I have to remove my own. Sorry.
Yeah, take your time.
Sorry, sir. Where is it?
Okay.
Not
Okay,
yet.
can you see my screen now?
Yes.
Yes.
I suggest to move to the full screen.
Full screen now, is it okay?
PowerPoint. Yes.
Okay. Thank you everybody for allowing me the chance to talk today. My name is Yusuf Rashid. I'm professor of engineering. I came from engineering and actually computational mechanics background. I am mainly interested in boundary integral equations, maybe for now for 30 years. And today I'm going to talk about a possible generalization of Newtonian gravity. I would try to be fast because I have something like 15 minutes and I will try to be as concise as possible. At the end of the day, I just left everything about the mathematics that I'm going to talk today in one of the links. I'm going to show it now. This is my contact. This is WeChat and WhatsApp. Anybody can contact me on this number. Before I start to talk, I want to have two main important points. The first point is, if I consider this is our universe, and this is, for example, a galaxy, and this is a black hole, for example, or something like that, and my choice was 4 points, as we can see now. And I'm going to do something artificial. I'm going to remove every celestial objects from this universe to be totally empty. When I do that, I'm definitely sure that all points are similar. All points are similar. So we have a symmetry of all points. Even our universe cannot recognize which point is which. Okay? This is the first point. The second point is, this is a very well-known Newtonian gravity, and this Newtonian gravity, we obtained it from observation. This is very, very important. Even in mechanics, our main postulation of rules, it came originally from observations. This is very important point. Okay, so what I wanted today is to make this equation work everywhere, near black hole, even when we have some additional gravitational field, anything. Okay, as I said, I left all of my talk on this link. I will start with the Gaussian version of gravity. This is a Poisson equation. This is a Laplacian, three-dimensional Laplacian. And what I'm going to do is to write the direct integral equation. What we have in the literature, it is always in direct integral formulation. Okay, it's a simple layer potential or double layer potential, but now I'm going to write this one in direct integral equation. We do this very simple. We take this equation weighted by certain function. In this way, we use the free space green function or fundamental solution, and we integrate twice to reach at the end of the day this integral equation. So this integral equation, we have the gravitational potential, some boundary integrals, and the particular integral here. If we differentiate this gravitational potential to obtain the gravitational force with respect to the source point, we can get this new integral equation, and we can differentiate inside the integral sign. Is not a problem because the level of singularity of the function allow us to do that. It's not a big problem. Coming back to this integral equation, when I used the suitable fundamental solution for the 3 dimension, I ended up to this equation. This equation, we have the derivative of the gravitational potential is a gravitational force and additional boundary integrals. This is Ri, this is a term. It is additional boundary integral over the boundary of our universe. And we end up to the particular integral here. If we compare this equation to the Newtonian, very well-known Newtonian law of gravity, we will see this is exactly the same. For a single unit mass, for example, we will have this row. This is the density or the mass of the objects, and the summation over all celestial objects. And this is the direction, unit direction towards the force. And this is r square. But we still have here additional term, which is Ri. This additional term is integral of the derivative of the gravitational potential over the boundary. Now, when we look at this equation, we knew from observation that the force is equal to this particular integral. That means the value of Ri is 0. This is always at all points inside our visible universe. Meaning, when we have a Ri equals 0, that means in the integral equation that our universe has no boundary, that our universe has infinite boundary, or topologically infinite. Okay, so this is the first conclusion, that from this equation, as far as this Newtonian gravity is working by observation at all points in the universe apart from some points, that means Ri equals 0. That means our boundary, the external boundary of our universe, is topologically infinite. Coming back near a black hole, for example, we claim that Newton gravity does not work near black hole. This is typically because of this term. This term Ri, it does exist. It does exist near black hole. That means when we have a black hole, for example, it introduces internal boundary to our universe. It is exactly like a spherical cavity inside our universe. So if we are able to compute this Ri, that means we will be able to make Newtonian gravity work near black holes. Even if we have two spinning black holes near each other, we can generate a combined surface for this boundary or something like that. And this is good also if you look from the general relativity perspective, because you will never reach a singularity. Okay, that because you will have something like a cut in the boundary of your universe or something like that. And this is a big question, because you have cut in the 3 spatial direction or the time direction. I don't know, to be honest. This is, I will leave it to general gravity guys. So this is our equation. Now we have the gravitational field, the Newtonian gravity, and this additional boundary term. And we talked about points where the gravity, the Newtonian gravity is working, means Ri equals 0, that we have infinite boundary or topologically infinite. And when we near black hole, we will have this kind of spherical cavity inside this black hole. Now I'm going to use the same idea for the index notation to represent the 3-dimensional figure using 2-dimensional figure. So instead of presenting x1 and x2, I will collapse both of them to x alpha. And x3, the same x3. And this is the celestial object we have, and this is a black hole now. So now, the 3-dimensional representation, we are able to represent it in 2-dimensional to allow us to understand or visualize more than the 3 dimension. I will come back again when we have this equation. When we have this equation and we don't have the value of Ri, we are apart from black hole, and still this equation is not working. Something when we have something like a flat rotation curve for galaxies or something like that. So we have additional gravity. The only way to have this, to explain this, that we will have additional particular integral in this equation. This additional particular integral from this equation will make us start to interpret this in terms of in the 3-dimension. If we look at the 3-dimension, we could be living in a 4-dimensional universe, and our universe is 3-dimensional, and we have nearby universe 3-dimensional also universe, and both of them affect each other by gravity in the 4th dimension. We can compute the gravitational field in the 4th dimension. It will look like this. I compute it and I left it in the note. I show it in the link, and you will have this additional field in the 4th dimension. And be careful, only here is the rho here in the 4th dimension. It is rho times the space in the 4th dimension to allow consistency in the dimension. So this is a generalized Newton law. The force equal to the traditional one we have it, plus additional boundary term, plus gravitational field from fourth dimension, and we can so on if we think that we go for 5 dimension and so on. But actually we care at the moment about the our 3 dimension, and the higher one is the fourth dimension. But we can generalize it in a straightforward way. This will give us a clue that these black holes, maybe it is closed as a spherical boundary, but it is open in the fourth direction. This is very, very important conclusion. I'm not going to move forward. I will stop at this point. Going to the conclusion, we generalized the Newtonian gravity. We discussed our universe boundary, whether it is external or internal, and even this is applicable for general relativity, considering we have a cut about the black hole in the spatial direction, but I don't know what will happen in the time dimension, I mean. And we demonstrated that we are living in 4-dimensional universe, and we have additional gravity in 4th dimension, and this is the note here is written here. And I presented in this note also a computational proposal. Once I have a measurement, I will be pleased if anybody has a measurement for the gravitational field anywhere in this universe. I will be able to compute this spherical cavity about the black hole or spherical boundary. We can compute the distribution of the masses of the celestial objects in nearby universes or something like that, once we have observation backward using deep learning or artificial neural network. And actually we are here in our team here, we are very expert in this artificial intelligence and computational mechanics. By this, thank you for your listening. If you have any question, I will be pleased to answer it.
Thank you, Professor Yusuf.
Okay.
Any questions? Okay, thank you very much for all, and see you tomorrow, inshallah.
Okay, thank you very much.